So, welcome everyone to the first session of the final day of FragMate 2024. In this session, we have three speakers. The first speaker is Oswani Ramos from University of Lyon. So, over to you, Oswani.
Hello, everyone. So, first, my first time in India since to you. So, thanks a lot for the invitation first. And second, and especially for the organization. So, it's really both the professors and the students, all the volunteers, you have done a really fantastic job. So, thanks a lot for that. So, and then, I'm coming from Lyon. So I feel obliged also to invite you there. So we are just 2 hours from Paris by fast train. And while Lyon is famous, but it's the capital of the French cuisine, and also is the place where the cinema was invented. So that was two highlights of Lyon. So this is the center, and just by crossing this really nice park, here is the campus of the university. We are in those two buildings here. And the experiment that you were just watching is here in this building. So this will be the outline of my talk. So I will be first doing a short introduction, a short motivation, and then two big parts. One focusing on some open issues of in scale invariant avalanches. Invariant dynamics, and then I will jump to the experiments, where I will first place some of the old results that we have, and then the new things we are currently doing. So, motivation, fractalized dynamics. So that's a little bit the subject of the conference. So, bridging across scales, and then we can talk about the same fractality, both in a space and in the dynamics. So in the space we have that. So we are large animals made of around 30 trillion cells, and we have to bring the oxygen to all those cells. So if I ask you to do the blumping between our nose and all the cells, of course you will build a fractal structure. And this fractal structure is a tree-like structure, like this one here. And it's exactly the same issue. We have to bring the water and nutrients to all the leaves, where we have the chemical process doing the photosynthesis. And for doing that, we have this fractal structure, bridging all the scales. And here, we need how to account for that. For instance, here we know that we have the trunk is one structure, and then we divide in 10 structures we can say there are 4 times smaller, and so on. So there are 1,000,000 structures that are 400 times smaller, and there are 100,000 small branches. And when we put all this together in a log-log plot, then we have this line, and the fit will give us the fractal dimension. All of those understand this quite well. So this is fractal dimensions between 2. Yes. This data is just, I did it last night, just put it like that. I'm just saying, imagine this is a trunk, and this is size 1, and this is those branches I imagine there are 4 times smaller, and then the other branches 40 times smaller, and the other one 400,000. And then you get something. This is just I did it by hand. There is no real data there. It's just to illustrate what is the fractal dimension, something that we understand quite well. And we know that, you just put 2.5 to get the round numbers. And we know that if we move, we can be between 2 or 3. If I tell you that this number is 4, quickly you will say, no, it's not possible. So we understand quite well fractal dimension, this number here. And we know that in this case, have to be between 2 and 3. Okay? That's also really clear. 2 is just 2 dimension, 3 dimension, and the 3 is between the 2. So that's something that we understand quite well. And then, considering dynamics, So here we have turbulence. You know that the energy is supplied as a big scales, just doing a turbulent flow. And we know that the energy dissipation is taking place at the really small scales, and there are dissipation across all the scales in the system. So that's something that we know in the forest. And in this case here with earthquake, which is similar. So the energy supply globally, we are moving the tectonic plates, and also the energies getting dissipated and the interface in all the asperities that are getting broken there. And the same, we can account for the energy that is released there, and then we have this power loss, where the energy that is equivalent to the fixing moment we have here, and then we have really clean power loss with an exponent around 166. But this is more difficult to interpret. It's like tell you, this is 1.67 or 1.8 or 1.2. So when we see this, we say we have many small events, large, just a few large events. It's like earthquakes. We are doing this independently of the exponent value we have there. That's you see we do since 30 years. Well, I will do a parenthesis to better explain that. Because this, we understand it quite well. We are used to talk not in terms of energies, but in terms of magnitudes. As I told you, this is Japan. All this is real data. This is Japan. And we see here that we have one magnitude, one earthquake of magnitude 7 and 8 per year, or we have one earthquake between magnitude 8 and 9 every 10 years. And so like that, if you are going to Japan for 1 month, eventually you can feel an earthquake because there are so many earthquakes of magnitude 6 and 7 between 1 month, and then you have high probability of feeling an earthquake. So then we see that this is the relation between, it's exactly the same data, this is just in energy, this is just in magnitude, and this is the relation between the two. And in geology, you are used to use this description of the phenomenon, and we see that the p-values are really around 1. And that's a big message I'm bringing here. But we'll see that later. But the idea is that, the earthquake data today is really good, and we have to use it. So, and then this is difficult to interpret, but this is really easy, and that's the thing we have to get used to. Okay? So those phenomena, well, those communities are used to have power loss since many, many years ago, but actually the idea that brought the physics community or the statistical physics community into this idea of scaling variant avalanches was the self-organized criticality, because Purbach was trying to explain all this fractality in nature by saying, okay, we have scaling variance in phase transitions, but the problem of phase transition is that we have to tune the critical point. We know we have magnetization, all the spins like that is low temperature, all the spins are disordered at high temperature. At some point we have the transition. This transition, we have really to tune it to the critical point when we see a transition, but in nature, no one is tuning. So the idea of Purbach was really nice. He's saying this point is an attractor of the dynamics, and the dynamics by itself will converge to this point, and illustrate it with a pile. So we are just adding rays, but itself, the pile will grow, and we will have avalanches of all sizes. Well, not all sand piles behave like that. The theory was kind of controversy. We see the title of his book for obvious reasons. But I guess we had to give credit to Purbach for at least for 2 things. First, for bringing the community of statistical physics to get interested in those scale invariant phenomena, which are really relevant, especially earthquakes, stock markets, fracture, etc. And second, also for fixing a little bit the tools. So now if we are trying to analyze the physics of the scale invariant avalanches, normally we are using the physics of critical transitions, critical dynamics, to treat that. And in my point of view, there are many open questions related to that. So concerning to scale invariant avalanches, and well, I will not talk about maybe about earthquake, but about experiments. So why we have this scale invariance? I showed you in the experiment we have scale invariant for 6 decades. In the experiment there is just 4,000 grains. So it's amazing. We will see that. Which is the origin of that is not totally clear. Are those exponents, are this dynamics is robust? Actually, no. We can tune the exponent values. And also many common features, all those systems like clustering, both in time and in space. I'm talking about aftershocks, foreshocks, etc. And also memory effects. We will see that we have some memory effects both in earthquakes and in our data. So that's something really important to understand. So about critical properties. So if those systems are critical, we should expect that they belong to a universality class, that those exponents are robust. And that's not the same with experiments. Okay? And also we will see that there are many experiments with exponents larger than 3.5. And that's a problem. We will see why. If you want to talk about criticality, maybe the best thing is to talk about divergence of correlation length, but it's really difficult to measure correlation length in experiments. So sometimes. So that's what. So there are many things to understand this part, and maybe the most I won't say interesting, but one of the most important questions in this field is it possible to predict the catastrophic events? Is it possible to predict earthquakes? Today, no one can predict earthquakes, but no one can say it is possible or not. And this is really important. So, there are some questions that I'm addressing in the series I'm doing in Lyon. So, I will pass to the first part, so some on open issues, and we'll see that there is important gap between theory and experiments. So, which is the exponent values to earthquakes, and this is really relevant. So the answer would be yes. And then following the same idea of critical dynamics, so this is a fantastic paper that is really amazing how they are to calculate all the exponent values of the avalanche distributions by using the randomization groups. It's like a 30-page paper just with calculations. It's amazing. And the results are those. So they analyze the exponent values of during the depending transition of the avalanches, and those are the results. So they use 3 different interactions like random field, random bonds, and random periodics. This is not really important now. The important thing is that those are the results. So we see that before dimension 4, the exponent values are different a little bit. That's also normal because they belong to different university classes. They differ a little bit in 3 dimensions, in 4 dimensions, and above 4 dimensions. So this is the critical dimension. So all the exponent values that we have, and in infinite dimension we have mean field. This will have mean field, and those are the results. So if we are doing experiments, normally experiments, most of them are in 2D. So we will expect having all of them around here. And those are the results. Well, I just put some experiments that claim a little bit the earthquake behavior. But we see that this axis of exponent is quite populated. So if you are a... Sure.
This upper critical dimension is from equilibrium statistical physics?
Yeah, that's the result of the applying the renormalization groups to calculate the exponent values in the dependent transition.
Okay, for depending transition. Otherwise, I was thinking for random field, the upper critical dimension is, different from 4.
Okay. Okay, that was in the dependent transition. And if we do, for instance, if we do several automata models like the sample model or the OHC model, etc., we have also the same. Then the critical dimension is 4, and we have the exponent values around here in 3 dimensions, around here in 2 and 3 dimensions, respectively. So anyway, so we, for instance, all those experiments or real data, well, everything is R2D. All those are in 2 dimensions, so we should expect having all the values here, and we see that the values are quite spread. So if you are a experimentalist, you will say, theory doesn't work. And if you are a theoretician, you will say, experimentalists, they don't know what they are measuring. And maybe they are right. So avalanche size, what is the right variable to measure? And that's really important, because we know that if we change, so imagine we have this power law describing our dynamics, but if then I define a new variable that is just a linear variable, imagine, to the given power, then we will have a new power law with a new exponent value, and then these new exponent values depends on just I just put like a dimension here, but we'll do the exponent value here. The message is, if you give me the exponent value that you want me to get, I can get it. So I will define my size of the avalanche as L to the power law 3/2, and then I will get the distribution you want. Okay? This is dangerous. This is dangerous because if we want to compare with something, we need to get a standard. And for that, it's really important to define which is the right avalanche size to measure. And in all the several automata models, including AC model, collection, etc. So the measure of the size of the avalanche is the volume of the avalanche, and that's the things we have to measure, and that's it. So the right, at least if you want to compare with those results, so the right definition of the avalanche is the volume of the avalanche. So here earthquakes are to the phenomena. The seismic moment, which is the equivalent of the energy, is just mu AD, and A is the area of the rupture. So this is constant value, this is really small value, and normally all this order of magnitudes in distribution is coming from here. And those are the results. It means that this value is the right one. And if this value is the right one, then maybe this critical phenomena doesn't explain them. So, we have a PhD working on that. I won't go any further on that, but that's alarm there. So, if we are using really critical phenomena in those systems, you should have this. We should compare those values to the exponent values we are getting, and if we are not there is a problem. So that's why I say there is a gap between the things we get from theory and the values we are getting in nature. So, and then, and one problem there also is that sometimes it's difficult to interpret what you're getting. So, for instance, here, all those experiments there, I would say they are claiming like earthquake behavior, one way or another. And those are, I just put the same here. I put all the graph of the power loss here, of those exponent values, and how we interpret that. And the idea is, well, yeah, they get this many small events, just a few large ones, and no characteristic scale, of course, and it's like earthquake. This is true. You will see that not really. So let's do the same that I did at the beginning. Let's talk about magnitude. Let's translate this into magnitude to understand what is happening. And here okay, this is real earthquakes. So we say that the B value is 1. So this is the equation linking energy to magnitude. In real earthquake, the B value is 1, and the ratio between magnitude 2 and magnitude A is 10 to the power 6. And we have this Gutenberg law here. What happens when we put the other values there? So those are the Gutenberg law that we have. We see that they are really, really different. And we can also say that. For instance, in Japan, we know that we have a magnitude between 2 or 3 every 5 minutes, and a magnitude between 8 and 9 earthquake every 10 years. So here I just put what happens is we keep the number of events and we change the exponent value concerning this distribution and see the difference. So this is real earthquakes. Well, that's experiments we showed at the beginning before the talk. Experiment you're doing in Lyon. But for instance, when I'm analyzing this exponent value, we will see that those events here are really, really probable. So one big event we will get after 80,000 years. So it's fine. However, if you go in the other direction, so this would be like the mean field value. So we will have a really big one every 3 months. And if we are really in the critical value for 2 dimensions, something around here, it's even worse. So we will have 1 magnitude 8 every 9 hours in Japan. So imagine, so we will be like that all the time. And then, for instance, sometimes we even get, so this value here, it means that here the Gutenberg is inverse. So we have more magnitude 9 than magnitude 2. So this is not earthquake. Okay. So there are 2 important issues there. So the physics is not the same. Well, let's start by the less important one. So if you want to convince the mayor of Tokyo that you have the model, you say, I have a model, but I have one big earthquake every 80,000 years. Okay, don't worry, so it's fine. And also you say, yeah, I have a model that will predict everything, but well, we have one magnitude 8 every 9 hours, and I'm not sure you will get the money. That's an issue. It's really different, but there is the most important one for us, and this is that the physics is different. So the physics of real earthquakes, so you get accumulation in the fault, you get a big earthquake, and then the fault have to wait for get the energy and generate the new one. If you're in this situation here, you cannot wait. So the energy has to be there all the time. So the energy is not coming from the fault, it's coming from the bulk. So the energy is available there all the time to deliver a big earthquake all the time. So the physics is really different. And in this one here, it's also really different because in real earthquake, the big ones are dominating the dynamics. In this scenario here, are the small ones. The small ones are dominating the dynamics, and the small ones have a problem because at some point we cannot detect them. So we don't know how many they are because there are too many, they are too small. But if they are dominating the dynamics, that's a really problem. So that's why I'm saying that all those earthquake-like phenomena or earthquake-like systems, they are not really earthquake live. We have to really be aware of interpreting well the exponent values. That's one message. And the second one is, so what to compare with? So now we're doing experiments, what to compare with? Well, normally we should compare with this one here, because the first observation that we have is we see that dimension is really important. We see that the difference between 2 and 3 dimensions is really important. Why? Because dimensions, just by the number of neighbors, put a lot of constraints to the dynamics. There are many loops in the avalanches in 2 dimensions. There are less loops in 3 dimensions. And above the critical dimension, you don't have any more loops. And that's why the dynamics doesn't change. And that's the sense you have in midfield that is equivalent to infinite dimension. So we already see that there is a big difference between those two. So comparing with midfield is not the right set. We should compare with this value and not with this value. And that's something, that's why I put this, when I put the experiment result, I put this 3D figure there, because there is a convergence of experiments showing 3/2 as exponent value. And normally it's really difficult to have experiments with big power laws that we can get really proper exponent values. So people are used to say, okay, that's the exponent value we should get, and sometimes we see an accumulation of values in the experiment, especially in the early times of the 20 years ago, that the quality of the experiments were less important. So that's a sin. And also there is another sin that we really have to be aware of. For instance, this paper is really preview for physics of 2018, also serious people. And look at what they're doing. So I say, okay, they know the relation between magnitude and energy. And okay, I say, if we know the big value is that, and then if we put then we will have 1.5. So they are really bending the statistics to get the big value here. I told you the value is 1, and it's really, really clear. And they say, okay, no, those values are really whatever. So those values here are exactly the same that Perbach was citing in his paper in 1989, where the quality of the catalogs were really bad, and when those people are unsure, they didn't know a lot about earthquakes. So today, this has changed. So the data is really available, and it's really easy to use, and it's really good. So you will get really clean power laws around 1. That means that those, when we translate this to energy, the beta values here are around 1.67. And this is, well, you can see the quality. So that's something we can really rely on. So that's a thing that I tell my students all the time. You try to compare with earthquakes, go get the data, and do exactly the same analysis in real data. Okay, to really compare with an experiment. And yeah, there are many different catalogs, and really we have to get the data because the quality is really good, and we can really trust this data. And it's really different from 3/2.
Somehow you are taking the pinning problem as the reference theoretical model for earthquakes, but there have been other models, maybe more appropriate to earthquakes, like the Burich-Lopov models. What could you say about the predictions of those more adapted to earthquakes models regarding exponents, etc.?
If we use this is a really important point. So I used the renormalization group. It was the right formalism, which we believe that the critical phenomena is the right description. That's why I started, okay, let's do it by the book. It's just critical phenomena, let's use renormalization groups, and those are the results we have. And they are the same if we use the sample models or OFC model, there is just a translation of the written path. If we change the model, of course, there are more better adapted models to earthquake than those, and that's also the message. I don't think that this is working. Then are those models critical? That's also a question. So one of the problems of the SOC is that all those definitions were really loosey. Where is criticality? Where is that was the problems, and that's why SOC was so controversial. That the rigorousness of the definitions were not really good. Okay, so for the main message that I'm bringing here is, okay, in my opinion, there is really gap if you use those by the book, those ideas of critical phenomena to explain earthquakes, and with the spotting values are really important. They are not 3.5; they are 1.67. They are larger than 3.5. If we use the formalism of renormalization group, you cannot get larger than 3.5. You see that for 2 dimensions, 3 dimensions, and then you get 3.5. It's an infinite dimension. So there is a problem there. So, and we are working on that. But yeah, that's the message today is, okay, we have the theory, and now we have some data that we can trust. An earthquake is a data that we can trust now because the quality is really good. And the things I would like to convince in the second part, I will be really quickly because is that now we are starting doing experiments with really good statistics that also we'll see that the data is really good, so we can trust it. Okay, so the experiment. So we saw already at the beginning. So this is the experiment. This is a really simple one. So it's we are just compressing and shearing really slowly. So we see that one period is 18 hours. So the linear velocity here is 5 centimeters per hour. So this is, we don't see when it's moving, it's really slowly because it's static. So we are doing this inside a cylinder. It's just a monolayer of discs that they are dispersed to work catalyzation. All these are photoelastics, so those are you see the stresses inside the system. So we compress with dead weight air, and then we rotate really slowly. And well, we see what happens in the fault. So there is a shear band that forms, and from the time that we start shearing, we start hearing crack all the time. So the system starts reorganizing and doing avalanches that we call LabQuakes. So we are putting here 6 acoustic sensors to record those LabQuakes, 2 for sensor, 1 here, 1 in the shade here, and well, that was the first version of we have all those cameras here. We have 24 cameras. That's the most difficult part of the experiment. We have to get 24 cameras to get one image like that. So that took PhD student to build that, to start analyzing that. And even that, this image quality wasn't good enough for analysis. So I had to change the whole setup of the whole cameras. And now we are getting really good images. And also here I put 2 positioning sensors to analyze the dilation of the granular faults. So now they have really nice quality in the image. And from those images we can get the network of the whole system, and then soon we will get the data. So what's the problem with this experiment is that the amount of data is huge. So we are running all the acoustics, all the force, all the 1D signals at 100 kilos because they are just plastic, so that's enough for the acoustics continuously during 4 days. So this is just half a terabyte, one experiment. And the images, we are doing this slowly every 2 or every 4 seconds during the whole experiment. And this one experiment is 60,000 images per camera times 24. So it's 9 or 10 terabytes of data. So one experiment is 10 terabytes of data. So it's really difficult just to handle. Okay. So that's been a lot of work just to handle the data. So where we are measuring, so we get a stationary state. Here we have the torque or the force. And of course, this is with respect, we have the force is increasing, and then we have sudden jumps, we have avalanches, we can define the energy of those avalanches. Associated with those avalanches, we have acoustic emissions, and by doing the wavelet analysis, we can get the energy of those emissions. And here we have, for instance, how is the position of the plate evolving in experiment of 60 hours, of course, and then we have also the ground resolution. So that's maybe the main result here. So we have here the distribution of energy of the acoustic emissions. We see that we have a really clean power law for 6 decades. So those event here have 1 million times more energy than the smaller one there, and they are like 1 billion times, 10 billion times less probable. So it's really amazing to get these dynamics just with 4,000 rings. So the complexity there is really huge. Well, if we do the mechanical ones, the resolution is smaller, but we have exactly the same power law for the mechanical avalanches. Yeah. If we compare this to earthquakes, so we get a really close value, and really close. If we saw the discussion earlier, so really close means that if we are talking about Japan, we will get the big one not every 10 years, but every 20 years. So the difference is not very significant. Well, that's just distribution of avalanches. Where, for instance, we also can analyze the time distribution of the events. And for instance, we put a threshold time here. This time. If we change the threshold, we will get a different distribution. And if we normalize, but the mean value of that, all the result will collapse in this master curve. This is for real earthquakes, and that's the state we have. So we see that the blue line is an exponential distribution. It means that there is no memory, and we see that for longer times there is no memory, but for shorter times the dynamics deviate from the blue line. It means that there are some memories of the past events. How we interpret that? Imagine that in Japan there is one big earthquake every 10 years. It means between 8 and 9. The fault remember during 10 years this event, the last one, and then forgets. So those are for real earthquakes. Those are for our experiment, also for different thresholds in energy. And this line here is not a fit, exactly the same one here. So it really have exactly the same dynamics. Also, we have Omori laws, so aftershock and foreshocks. So here there is a difference. We don't have too many events. So in real nature, we see one main shock and the aftershocks. Here we had to make an average. So we are hitting a little bit. So all the rest are really quantitative, exactly the same dynamics. Here there are more qualitative. I think we did just taking a slide the window and analyzing the good temperature value here and see how it evolves. And so in nature, we know that there are variations before a big event, and we also see that here. And also we see it's also really interesting, for instance, when in those 2 point here, just before the big one, we see there is a reduction of activity in average. In average, we see that there is a silence between the really big ones. So the system have to breathe his breath to get really a lot of energy, and then there is a big event. So sometimes in some really big earthquake, we also get this reduction of activity before the big one. So that was the main results also of this part. So what we are doing now, why it's important is we have exactly the same dynamics. That means that the physics behind may be the same. So that's the thing we're trying to understand. It will be much easier to understand the physics of this small granular experiment than real earthquakes. So that's the thing we're trying to do now, try to change the parameters, trying to analyze the memory effects. Of course, memory effects are in the structure. Now we have it. It's possible to predict the events. We'll come back to that now. Of course, it's also important to separate what is universal and what is particular for the earthquakes or for the granular faults. And here we have an important difference. We are much faster than real earthquakes. So in 2 days, we get the equivalent. In 2 days we get the equivalent of 150 years of magnitude larger than 2 in California. And this is really important because since a few years, the artificial intelligence is really working hard to try to predict earthquake, but they are just 10 years of data, 10 years good data, and we are trying to predict one that is coming every 150 years possible. So here we have 150 years in 2 days, and now we are running for 4 days, so we have a lot of data, millions of events, so we can really play, trying to explore all the possibilities, trying to see. So it's possible to predict them. So that's Olivier, that is our specialist in artificial intelligence, and Luis, that just finished his PhD last year. So we were inspired by this paper where they really were able to predict the coming of the next LabQuakes. But here we see that it's really almost quasi-periodic and almost all the same size. So it's really easy to do it. Why we do this we did exactly the same. We started doing that because it was really well documented. Impossible. Why? Because it's really difficult to say to a machine learning algorithm that this is big and this is small. The physics between this point and this point is the same. So it's really difficult to say this is big and this is small. There is no characteristic length. So it's analyzing scaling bind dynamics with artificial intelligence is a challenge. That's something that we are doing now. But there is a hope. If we separate the big ones and the small ones, and the things we do is that, we take the time series, and if we see a big one, we just take this chunk before every one, and we put it in the new time series, and we continue. And if there is a really calm one, we get it and we put it after the other one, and we roll that, and then we have a new time series just with those events or those events, and in this case, we can predict. So here is this matrix to say, okay, we see that we have we took 1,000 like those ones, we get 24 of those. Out of 24, we are able to predict 13. So it's really good. I mean, if we really separate those in two, we can there are some prediction there. So there are some information here that there is an incoming big event. So that's a hope. But from the time we start trying to bridge the gap between the two, we lose everything. So we are working on that. 5 minutes, 5 minutes, so we really go quickly here. We have many projects, ongoing projects. There's a really surprise. Negative avalanche and anomalous dilation. So I told you that we are measuring the force and also the position, and the things you expect is a smooth increase of the force, a smooth dilation, and suddenly, puff, an avalanche. And this avalanche should contract the system and release the energy. And look at that. So that means we should get that. The torque in the avalanche, the torque will suddenly decrease, and the height will suddenly also decrease. And sometimes we have that both are suddenly increased. Also, we have the mixing of the two. So the intuitive part is this one, where we have these sudden jumps, sudden drops of energy, and sudden drops of height. But we see that the four are quite populated. So those two are kind of easy to understand because, well, this is the energy we are measuring here. And, well, we know we are pushing and shearing, and then the force chains are trying to put it there aligned with the force. And then we can really make a really simple hypothesis that just replacing force chains that is wholly resisting with a new one. And yeah, just by changing the angle of the force change, it's really easy to explain those two, because it's the new one is more vertical. It will favor it a jump in height and less force, and then is this force change is replaced by a more horizontal one. Well, this is unstable. This is unstable. That's why we don't see too many events here. Is the new force change is more horizontal, then we will favor the force and then the height will decrease. So we can explain those two, but this one is really interesting. And what is happening there? So we'll just tell you. That's the most important one. Is the problem is the fall is really under compression, and locally we have a collapse, but the things we are doing is that. And as the result of the avalanche, the fall arrives in a configuration when the energies suddenly increase. We have more energy than before, and also we delayed. So we are in a configuration that is dangerous. So we have been discussing with geophysics. We have a lot of collaboration with geophysical people. Say, yeah, that's can be relevant for us because, of course, acoustics is only positive. Also of those events, we hear LabQuakes. We say, okay, the fall relax, but no, this is really dangerous because the force increase in energy. That's also we are discussing with geophysical people. So, well, that was just to verify that those hypotheses are good, and they are. Well, those are the conclusions. So it's very important to remember all different exponent values can reflect different physics. It's not just we have a power law with a given exponent value. There are small ones, many small ones. Sorry, a lot of small ones, just a few big ones, and it's like earthquakes. No, it's not like that. For me, there is a clear gap between theory and earthquake data. And now earthquake data is quite reliable. We had to really get that for a reference. Well, and we are working on an experiment that really good quality data, and we had the result look quite promising. We are both the analogies, the dynamics. I haven't talked about acoustic localization, but well, we have many projects going on this project. So well, those are there have been already three theses on this project. Also, Ramon that was there as a postdoc around 10 years ago. So Olivier is the artificial intelligence guy. He's helping with building the experiment. Also some collaborations abroad. So that's the team now. Well, not her. She was just visiting. Well, thanks a lot for your attention. It's been really a pleasure. And just to finish, well, in Lyon, in December, around the 8th of December, we had the Fête des Lumières, the Party of Lights, and it's really, really nice. And before this Party of Light, we are organizing this traffic and granular flow in Lyon. So also an invitation for you to come. Those are the subjects: granular, collective behavior, traffic, and pedestrian dynamics. So thanks a lot for the 4 questions.
Yes, time for questions. So, is there any effect of the curvature on the dynamics that you are seeing? Your system is like, no.
Normally, it doesn't see the curvature. For that, so the grains have to be small. But no, normally we don't see any.
Not really. So, and how is the confinement like? So
It's like a 2D cell. So grains are the disc has like 4 from millimeter, and there is a small gap to avoid that they.
Okay.
Of course, they touch a little bit the walls, but so those are really hard plastics, and that's why we put a lot of weight. Because if we put a lot of weight, we favor the force in this direction, and then friction is less important. Of course, there is also friction. It's fair.
Is it possible to make photoelastic spheres? Has anyone tried, like,
Yeah, actually, so this experiment is 2D. So the friction is are all things that discuss like that. So the things that are important for us is this the flat part, and also friction is always 2D. So earthquakes are 2D, so that's fine for us. And the problem with 3D is that you get the stairs. Well, it's more difficult to everything, but they also block. So when I started doing this experiment in Oslo many years back, I was using spheres, and it didn't work. So because it blocks. When you put the weight, the spheres do like that, and it blocks. So we had to get really proper 2D, and for that the weight helps, because you force everything in this direction, and then of course there is friction, but it's not really important.
Yeah. So and also, like, your system is 2D, right? I mean, does the dimensionality matter, like, when you're looking at those exponents and all?
Yeah, the system is 2D. Yeah.
Okay. So whatever, like, the exponents that you are showing in the beginning, like, they were for 2D systems. I mean, I did not get this, like, connection, because if you the real earthquake data, it's for a 3D system.
Friction is always 2D.
Sorry?
Friction is always 2D. This is an earthquake. This is 2D problem.
Fine. Thanks.
Thanks, Osvani. I was just wondering, when you talk about prediction, I mean, at the beginning you said that you observed some kind of gap of activity before getting large events, especially large events. Then you talk about this method by machine learning techniques. I don't know, I mean, if you were able to open, let's say, the black box, what you would expect to find there.
And so far it doesn't work. The artificial intelligence. But all the things we did was just with acoustics. And of course, the analysis you're doing is putting inside all the signals, and I sure we get something else. But yeah, with acoustics, it's not possible. But acoustic is 1D, and then you get to the acoustic emission. And the hope is that before the big one, in the noise, there is some information about the structure, because of course the structure is important. The structure, we have it. See, just we did one. The structure is there. We don't have it yet. We are trying, because I show you an image, but we are having 60,000 images. We cannot do this by hand. We have to be 100% sure that all the algorithms that we have are really robust, because we cannot check everything how to do automatic. The point is so far we have done those acoustics, and with acoustics, we don't get any prediction that is relevant. And also this silent before the big ones, that was also with acoustic, but no, we don't see any prediction capability there. So far we don't get anything. And this is also in average. There is a big difference between something that is in average and something that happens regularly. Also, for instance, in the dilation part, we have one paper already on that. And the name of the paper was trying to predict with dilation. We know we are sharing a granular system. It will dilate normally before the V1. And it's true. In average, it's doing that. But the different realizations are really different. And it's really, so far, we haven't seen to explode this average and try to see in the different realizations. So it's really different. The message is really different to see social in average and get the prediction out of that. That's the message. Because we are physicists. We are used to say we get social in average. The correlation is possible to predict. No, it's not so easy.
So another question, you mentioned that you had the intermittent times with this exponent 0.3, and then you show the aftershocks as well. You had an exponent 0.8 and another one with 1. I don't know which one was foreshocks and aftershocks.
Aftershock was 1, and foreshock is really, well, that's really an average. You put all the data there and you see something. But you cannot get any prediction out of there either, so it's not...
You mentioned the possible importance of memory in this system. I understand that this system is a thermal, so somehow it is deterministic or disordered. I think it would be interesting to check for memory properties to do cycles. So I was wondering, to check for memory, you have to come back somehow, and see whether the system remembers or not. So is your device able to turn the opposite direction?
Yeah, of course. So that we have many questions concerning to that. The idea was we are stuck analyzing the images. That's a big problem now. But yeah, we can stop. We can reverse, and that's also that we want to do is, for instance, the origin of aftershocks. In geophysics, we don't know if it's a relaxation problem, or this is just that the system is broken, and then we continue pushing. And then in real earthquake, we cannot stop. Here, we can get the B1, stop, and see how the relaxation. And also we can reverse, and we can
reverse and check for the determinism of the trajectories. No?
Don't believe it.
This is upscaling from the microscopic to the macroscopic machine.
Any other questions? Yes, Arch.
So 2 quick questions. First, the beads, Osmani, are you making them or do you buy? The 3D printed, and they are photoelastic materials like from the
By chance.
resin. Okay,
Yeah.
good. And so you showed that lots of people were trying to compare apples and bananas in a sense, right? Like measuring different things, and that's not what the prediction of the exponent 1.5 really was. You could get like an exponent if you define what you showed, right? Measuring area instead of volume. Why did that happen? Why so many of us have like compared things that we shouldn't compare?
Yeah. No, that's a joke. But the main issue is that it was really difficult to get good quality experiments. So as I told you, we have one experiment is 10 terabytes of data. 5 years ago, it was impossible to do that for a small lab. And also, earthquake data, it wasn't good. Like 20 years ago, 30 years ago, it wasn't available, it wasn't good. So we didn't have any experimental or real data to hold, to compare and to guide the theory. So the theory evolved, and the experiment were trying to say, okay, yeah, I got the 3.5, I will get 3 houses, that's good. That's my opinion. And now that's why I insisted. Now we have really good data in earthquakes, And this is really reliable and easy to analyze, easy to. And also, we are starting to get experiments that with really solid statistics, that we have 6 order of magnitude is really clean. So there is no doubt there is 167 or 1 is not 2, it's not 3, it's really this value. And that's why all this the disparity of results. And that I guess we didn't have the experimental capabilities for doing scaling variant avalanches properly.
I have some questions actually. So is there the exponent depends on the strain rate at which the plates are moving? You told that it's very small, but is there any upper limit of the strain?
We haven't checked that yet. We know that we can tune the exponent value. First by accident, because we changed some stuff and then the exponent value changes, and we were happy or not because it was uncontrolled. And now we are trying to change we know, for instance, if we change the weight, it's robust. If we change the stiffness, it changes. So it's like that. So there are parameters that really can modify the exponent value, and there are parameters that are robust.
So in that,
the rate we haven't changed yet, but that's something that are really easy to change.
and I also believe the beats are monodisperse, right?
No,
Dispersive, okay, from a distribution or something.
And also the top and the bottom, they try to get a square structure, and so even with monodisperse bit, is okay, because they will try to get hexagons crystallized, but the bottoms are trying to get a square, and this will try to disorder. Disorder is the key, of course.
So last question from me. So in earthquake, there are lubrication also between the plates, right? In these beads, if you put some silica gel or something, are you using that? Will that change the exponent or something, introducing the lubrication within it?
I know. As I told myself, no, I would never put a liquid inside. It's already very difficult, and the physics is already there. That's why. It's I get without any liquids, the good statistics, it means the liquid is already there. So, or the liquids is not really. Well, it's not true. The liquids is really important but in geophysics, but the liquids is already there, because we get the right exponent values, the high dynamics.
Any others? Okay, so if not, let's thank the speaker once again.